Good afternoon, everyone. So I am Marinho Barcelos from University of Waikato, New Zealand. So this is the measurement session. The session has 4 awesome papers, one of which is the SIGCOMM'24 Best Paper winner. The 4 papers have measurement in common, but they measure different types of networks and address different measurement problems, like data centers, ISPs, or the whole internet. So the first paper, Zoom2Net, is about a transformer model that makes telemetry imputation from coarse-grained signals possible, improving imputation and increasing the accuracy of downstream tasks. The second paper is an experienced track paper, which describes IDP, a system that collects NetFlow data from all border routers in a network and identifies at fine-grained the sources of traffic, something that BGP cannot do. The system has been in operation for 6 years at a major ISP. The third paper is GIL, or the next generation of BGP data collection platforms. The paper describes an approach to identify and eliminate redundancy in the stream of BGP updates provided by different vantage points to BGP collectors. One of the cool insights was the definition of contextual redundancy. The fourth and last paper presents M3, a system that uses machine learning to predict data center network performance and specifically flow completion times. A relevant problem since traditional packet level network simulation do not scale for large data centers. So the first presenter, Zoom2Net. Is she here? Oh, yeah, you're right, okay. So let me introduce Zoom2Net, Constrained Network Telemetry Imputation. The paper is going to be presented by Fengchen Gong from Princeton University. She is a second-year PhD student there, and research focuses on improving network management by incorporating machine learning and formal methods. So the floor is yours.
Thanks, Marino, for the introduction. Today, I want to tell you about how we can zoom into network telemetry data just like we zoom into images. Network management is challenging and also includes various critical tasks, such as debugging network incidents, detecting attacks, and also planning the network through longitudinal analysis. All these network management tasks rely on monitoring data collected on network devices in the data plane. Because the management task performance depends on the quality of monitoring data, we want network monitoring to be general, cost-efficient, and of fine granularity. General means we can collect multiple time series signals altogether in a straightforward way. Cost efficiency means we want to do the collection on just commodity hardware. And fine granularity means we want to capture the short time scale events. However, as networks and workloads scale, it's becoming more challenging to collect fine-grained telemetry, and also store and processing them is also becoming more challenging because of hardware constraints and storage limitations. Oftentimes, operators are only presented with sampled data, which is coarse-grained and also unreliable. Network community has come up with different approaches, but it is hard to satisfy all 3 requirements at the same time. Let's see some practices. Mirroring traffic from the routers to collectors can satisfy generality and fine granularity because it enables the operator to run any customized queries at any granularity. But mirroring requires expensive and customized hardware for the significant bandwidth and processing speed. Sketching or other probabilistic data structures can help collect fine-grained telemetry in cost-efficient way. However, they are only designed for specific per-flow tasks, such as identifying heavy hitters. So extending it to some other tasks is not straightforward. Tomography can help infer unmeasured metrics from the measured ones, but it requires linear relations between different signals and also known network topology. It's not generalizable enough. Lastly, as I said before, sampling is the most common tool that operators have access to, but it is coarse-grained. So instead of improving the hardware or coming up with more complicated algorithms, we propose to add a software layer to recover the fine-grained telemetry from the coarse-grained versions. We call our work Zoom2Net. More specifically, consider a network system that can be described by a set of fine-grained time series. Now, there is a monitoring infrastructure that senses this network system by applying some sampling functions on the fine-grained time series to output the coarse-grained versions. And then, given the coarse-grained measurements, the goal of Zoom2Net is to recover the fine-grained time series, and then this can be used as input to various management tasks. Actually, interestingly, our imputation problem is analogous to image super-resolution, which relies on pixel correlations. But I know some of you will have doubts. Why would this ever work? Let's see an example together. Here we show length of 2 queues on a network switch over time at fine granularity of 1 millisecond. So Q1 is a bursted queue, and Q2 is a consistently long queue. These 2 queues look very different. However, if we apply the sampling function, meaning taking the maximum over the 50 milliseconds, actually the 2 queues look similar or exactly the same. Now, looking at this example where the coarse-grained version of the queue length are exactly the same, it seems impossible to correctly recover what is the fine-grained version of them. But if we look at auxiliary signals, meaning aggregated packet drops and packet sent, actually the 2 queues look very different even at coarse granularity. Indeed, the long-standing queue would cause more packet drops compared to the bursted queue. Therefore, we can use the auxiliary signals to help impute our fine-grained queue length better. So back to our question, why would this ever work? Our answer is we can leverage the correlations among different time series and to impute what has been missed when we do the sampling. And the correlations can constrain what the fine-grained time series would look like. Although these correlations kind of are obvious, but they can be very complex, so that it could be not easy to model them in explicit form. So we ask machine learning to help us do this. More specifically, we use this model transformer. It is a typical model for analyzing sequences of words in natural language processing. It uses attention mechanism to discern how each word in a sentence is related to all the other words. Now, in our example, we will replace the words by our time series data. And to output the fine-grained data, we add the linear layer on top of the transformer encoder. All right, now a strawman solution will look like this. We have access to some small set of data, which is fine-grained time series. We can downsample them to form our coarse-grained measurements. Now we can use these coarse-grained, fine-grained pairs to train our transformer. And at the runtime, given a new coarse-grained time series, which we don't have fine-grained version, we can use the transformer to impute their fine-grained time series. So this kind of looks very straightforward as a typical ML solution, but actually the strawman solution does not work, and we face 2 main challenges: no correctness guarantees and ambiguity. So we know ML model doesn't have correctness guarantees. So why operators would trust an ML model over real measurements? In fact, we find out or observe that the imputed time series from the strawman solution might be inconsistent and even incorrect. Let's see an example. Here we show the coarse-grained measurements, which is maximum queue length over 50 milliseconds, and then which is also the input to the strawman solution. And then the orange line is what the strawman solution would output, the fine-grained queue length. This is embarrassingly wrong because the imputed queue length does not reach to the maximum value at all. So there is a critical need to incorporate such knowledge into what the transformer is doing. In fact, we have pieces of different knowledge that we want to incorporate. We categorize them into two types: measurement knowledge and operational knowledge. Measurement knowledge meaning the imputed fine-grained time series should be consistent with our coarse-grained measurements. For example, if we apply the maximum sampling function on our imputed fine-grained queue length, we should get the maximum coarse-grained measurements back. And for operational knowledge, it captures the correlations between different signals according to the algorithms we use in networking. And they can be expressed as explicit form. For example, we say for the sum of concurrent queue length across all ports on a network switch should not be more than the total buffer size. We represent these knowledge into equality and inequality constraints. And next, we want to incorporate these constraints into the loss function so that we can tell or teach the transformer to output consistent results. Specifically, we add constraint violations into the loss function. And to better train this model using this loss function, we adopted the augmented Lagrangian method, which adds this lambda as weight to the constraint violation. And this lambda is updated based on how much constraint violation for this ML output. So what this means is if an ML output is violating the constraints by a higher amount, the weight of this violation in the loss function is also high, and it will cause more effective minimization. So through iterations, the transformer will learn how to minimize the constraint violations and satisfy the constraints. But incorporating loss does not guarantee the satisfaction. So we add this constraints enforcement module to further correct our ML output. Inside of this is an integer linear programming. We define variables to be fine-grained time series, and we use the equality and inequality constraints we defined previously. And then the objective is to minimize the total difference between the original ML output and the corrected ML output. So this is for the first challenge. Now, the second challenge is about ambiguity of coarse-grained time series. At high level, this is like we expect ML to output different things, but for the same input, which is fundamentally impossible. Let me explain this. So in this example, the two queue lengths, we show the fine-grained of two queues, and they are different because the bursts happen at different timestamps. However, unlike previous example, here we cannot use the correlations between auxiliary signals because they are also identical. This can't happen because the coarse-grained measurement is too coarse, and this is bad because not only we cannot impute correctly, but also the transformer will have a hard time to converge. Now, the insight to solve this is to refine these collision instances in the training data set, where the coarse-grained measurements are very similar, but their fine-grained time series are very different. For Zoom2Net to work, these collision instances should only be a small subset of our training data. And then for the refine module, what we did is to change the training so that Zoom2Net can impute any version among instances with identical coarse-grained input during training. All right, now let's look at how performant Zoom2Net is. We evaluate Zoom2Net in multiple management tasks using public dataset. The public dataset we use it as fine-grained time series, and we downsample it to form our coarse-grained measurements. In our evaluation, we want to ask two questions. First, how accurate is Zoom2Net imputed time series compared to the ground truth? And secondly, how useful is Zoom2Net imputed time series when it's applied in management tasks? We compare with 4 baselines: KNN, pure coarse-grained data, plain transformer, and an ML-based imputation model, which for time series data. I'm only talking about one case study from our paper. We use a data set and management tasks from paper published by Meta. Here, the goal is to impute 1 millisecond link utilization from 50 millisecond coarse-grained measurements. And the auxiliary signals include retransmitted bytes, incongestion bytes, and connection counts. For the first question, how accurate is Zoom2Net? We look at 4 different metrics: MSE, Earth mover's distance, which reports the distribution difference, autocorrelation, and 99th percentile. We report normalized relative error to the ground truth. Here we show that Zoom2Net achieves 33 to 53 better imputation accuracy than the other baselines. And for the second question, how useful is Zoom2Net? We use the imputed time series in the management tasks reported in the original paper. These tasks relate to burst characterization on link utilization. So given a fine-grained link utilization, we want to ask about burst height, burst duration, and burst volume. Here we show that Zoom2Net improves management tasks by an average of 38% than the baselines. Lastly, we investigated the effect of zoom-in factor on the performance of Zoom2Net. So we experimented different zoom-in factors from 25x to 100x. What we found is that by increasing the zoom-in factor by 50, the imputation accuracy and management task performance only degrade by 0.4% and 7%. All right, so coming back to our 3 requirements for network monitoring. We say Zoom2Net is a practical network monitoring tool that satisfies all 3 requirements at the same time. Zoom2Net is cost efficient because it is a pure software solution without any hardware changes. It is generalizable because it can be applied to different signals if they're cross-correlated. It can help increase granularity of the time series data by up to 50x. With that, Zoom2Net is available online, and I'm going to conclude my talk and open to any questions.
Questions, please.
Hi, amazing talk. My question is, how granular can the original data set be? Did you experiment with, like, for example, larger sample intervals? And when does this break down, I guess?
Yeah, so I think it depends on really the data itself. If the data is like changing very frequently, then you need a more, the coarse-grained data should also be sampled frequently. And so we have a way of, so we have a module in the paper that's telling you how certainty the ML model is about outputting this time series, fine-grained time series. So you might be inferring from that, like how certain that is, and to see if your input is coarse-grained enough or not. Yeah.
Thank you.
Thank you.
Hi, that was a very great talk. I think you may have just answered my questions. You mentioned the issues that one coarse-grained metric, a time series, may correspond to different fine-grained time series. Mm-hmm. So I was just about to ask, what is the mechanism for Zoom2Net to inform the user about how confident it is about the output in case of ambiguity?
Yeah, that's a good question. So yeah, the confidence or certainty model I just talked about can be one way to infer that. And then we have this mechanism where you can find the collision instances. And these instances should only be a small subset of our training data. So if there are too many of these collisions where all of them have different a similar input but different outputs, then that means we're going too coarse grain. Yeah.
Okay, thank you.
Thank you.
Marwan.
So thinking, this is frighteningly cool. Thinking about the future, have you given any thought to things that are not time series, strictly speaking, like event-based events? Oh, you understand the question?
Yeah, that's definitely one. Like, it's the abstraction. Like, what can we impute? So now we're imputing time series data, but is it possible to impute, recover the events that's happening given some coarse-grained measurements? If that's what you're asking.
Roughly speaking.
Yeah, that could be one direction that we can go forward.
Okay.
Yeah.
Any other questions? Well, I've got a question myself. Well, we have time, so if you want to fire another question, that's welcome. So my question would be, you rely on fine-grained time series data that could be collected from devices. You just say that it's not feasible to keep that data. Mm-hmm. But in certain cases, like a volumetric attack, as you use in case studies, you may not be able to collect all the signals, everything. So have you considered such scenarios, or how much data do I need for a problem? Both sides, considering what you can collect from devices and how fine-grained you can go, or you need to go with Zoom2Net to actually make accurate imputations.
So if I understand it, one question is how fine-grained, what is the fine granularity that Zoom2Net can achieve for some?
Yeah, if you cannot collect, a volumetric attack, you may not be able to collect fine-grained data, because the volume is too high.
I see. Yeah. So we do assume we have access to a small set of fine-grained data. This can be done using some, measuring techniques, but it's just going to be lasting a few seconds, maybe a very short time. So it's doable. And for the attacks, it is possible that we will not be able to collect these attacks because they happen once or not that often. Yeah. Thank you.
Great, thank you very much. No, Matt. Please, Matt.
Hi. I was a bit confused by your evaluation. It seemed like you were evaluating against the coarse-grained data, but isn't the evaluation criteria you should check is how well you're replicating the fine-grained data?
So the goal is to show what we imputed, the fine-grained data, when we use it, it's better than we use the original coarse-grained data, say in the management tasks.
So shouldn't the relative error between what you've imputed and what actually happened be the metric of interest? Because otherwise you don't know how accurate it is. It's as accurate as the coarse-grained data, but it's the fine-grained data that you actually care about as the outcome of your effectively compression system.
So we're not using the coarse grain directly. We use this iterative imputer, which it's a linear regression model that can expand this coarse grain into the full length of the fine-grained time series. So it's not exactly the coarse grain, but it does have the coarse grain measurements inside of it. And then we compare these expanded fine-grained with the imputed Zoom2Net results. Yeah.
Thank you.
Thank
Thank
you
you very much for the questions. We run out of time. Let's thank the speaker again.